So we're going to start with the cyclic stress strain curve, and we're going to continue cycling until some stable behavior appears. So let us repeat this cycle, in other words, loading between a max strain and a minimum strain many times, and let's see the type of stable loop that appears from that loading. Now, when we say many, well, it depends on the material. So many might be just something of the order of 100, so 90 would be of the order of 100, or it might mean something like 1500, more than 1000. That would be of the order of 1000 cycles. But eventually, many metals, let's say, eventually will display a stable cyclic behavior, and that's what we want to depict now. So to depict that behavior, let us again draw our stress strain axis. So this is our strain, and that's our stress. Okay. So we're gonna cycle the strain between a minimum value, okay, and a maximum value. And the mean is going to be 0, as we mentioned earlier. And what we've said is that if the mean of the strain is 0, we're going to assume, and it's not a bad assumption in most cases, that the mean of the stress is going to be 0. So in other words, when I cycle the strain between some maximum value and some minimum value, the stress likewise is going to be cycled between some maximum value and minimum value. So let's depict those limits with 2 lines as such. Okay, so this here is our maximum stress, and this is our minimum stress. Okay. What I'd like to also depict additionally here is a slope that is associated with the Young's modulus. Again, I'm going to exaggerate that slope and draw it as though it were very, well, let's say not so steep at least. So let's draw that to be something like this. So that's going to be a line of slope Young's modulus, and also going to draw a line that is parallel to that one over here. Okay, so that's our slope with Young's modulus 1. Okay, E is our Young's modulus. Good. So now we said that when we cycle stress versus strain many times, eventually one observes that this red line approaches a limit behavior. And in that limit behavior, the loop is closed. In other words, where I start at the maximum strain has a certain stress. When I go back, it turns out I come back to the same stress. There is no difference. If there is a difference, then it means that I haven't reached the limit or the stable loop. I need to cycle further. If I'm at 100, I need to go up to 500 or 1000 until the loop closes. And when it closes, I reach a limit. I reach the limit behavior, and the limit behavior is going to look like this. So let's say we are at the maximum strain and we are dealing with the maximum stress, and we unload. Let's unload on an elastic line. So unloading is elastic, and we unload until we reach a certain value of the stress at which we start to deviate from a linear behavior, which means some sort of plastic deformation is going to take place. So let's depict it with such a line. Okay, And then we reach the minimum strain at which we observe the minimum stress, and then we start unloading. And unloading is again elastic, and it's elastic, therefore on a line, and we unload until it turns out there is again some deviation from this line at some point during reloading. So when we hit zero stress, it's completely unloaded. We now push the strain even back more, so the specimen has changed its length. I push it back, the stress becomes tensile, there's a deviation from this line until we reach that point. And then if I were to repeat the cycle again and again and again, it turns out that we always rotate on this same cycle, which is the cyclic stress strain curve. And unlike a elastic loading where I go back and forth on the same line, in the presence of such significant plastic deformations which I observe from this not straight line, right? So there's significant hysteresis. So the loop is closed, but there's a net area inside the loop. So this is alternatively called the stable hysteresis loop, or the stable cyclic stress strain curve. Eventually we understand that this is the behavior that emerges after many cycles of loading and unloading between a max strain and a mean strain. Again, zero mean strain we are assuming corresponds to zero mean stress. So now let us try to interpret some of the quantities that we are seeing in this plot. So first of all, the strain goes between some max value and mean value. So therefore, this is the range of the strain, okay? And the range is always twice the amplitude. So here, this is plus epsilon A, and that is minus epsilon A in the present case, because the mean is equal to 0. Let's make a note of that here. So similarly, we have the range of the stress so delta sigma, which is twice the stress amplitude, again for the same reason, okay? So this is plus sigma A, that is minus sigma A. Okay, good. Now next what we can note is the following. Now suppose I was in a stage of looping, and I looped back and came back to this point. Now notice what this point means is that there is no stress, so I have removed all the load on the specimen, but the overall length of the specimen is not, the strain is not 0, which means the specimen in fact is negative. The specimen is compressed somehow with respect to its very original state at which I started doing this experiment. So at this stage it had an original length. Now I am at again a point where there is 0 stress, but the strain is negative, so the length is smaller compared to the original length of the specimen. So therefore we can see that there is some permanent deformation in the material, and that permanent deformation is negative, so there's a negative plastic strain. And in that region, if I were to come back to this point, there would be some positive plastic strain. So overall, I see that if I go from this point, suppose, and I keep loading at a state of 0 stress, and suppose I take this specimen and I load it, I reach max strain and therefore max stress, and then I unload back. And I come to this point where the stress is again 0, but now the overall change in the length is positive compared to the initial one, or as it's associated, the overall change in length is associated with this amount of strain with respect to this state. So this distance over here is associated with permanent deformation. And this distance, when I follow these parallel lines, is a portion of the overall strain. So there's the overall strain that we are imposing on the material, and that overall strain has a portion that is associated with permanent deformations, which we had always indicated earlier or defined to be the plastic strain. So this is permanent length change. And therefore, what we are going to now say is that this portion, this amount of the total strain, that amount exactly, is equal to a change or the range of the plastic strain. And the range is always twice the amplitude. So let's call that twice the amplitude of the plastic strain. Okay. Why again is this plastic? Because I start from zero stress during a portion of the cyclic loading, and I go back to zero stress, and therefore this is the permanent change in length that I impose on the material, or it's the permanent change in the strain, and therefore that is associated with permanent length change, let's say. So if that is the plastic portion of the strain range, the remaining portion naturally is interpreted as the elastic strain, which is again twice the amplitude of the elastic strain. So from all of this discussion, what we are concluding is a relation that we are already familiar with. Already we had proposed much earlier, based on the physics of the problem. Well, we said that if we load the material, the total strain is decomposed into a portion that is recoverable, which we called elastic, and a portion that was permanent, which we called plastic strain. Now we impose the alternating strain on the cyclic stress strain curve, the stable hysteresis loop, and we observe that some of it is elastic and some of it is plastic. So the total alternating strain component is decomposed again into elastic and plastic parts. So this is the first observation that we extract from the cyclic stress strain curve, and it's comforting to see that we are already familiar with it. Now, the second idea here is also going to be actually quite familiar. And what we are observing here is that, well, clearly, this is the total range of the stress, and this is the slope of this line. And when I concentrate on this triangle over here, right, that triangle, base is twice the elastic alternating strain, and this is twice the alternating stress. Therefore, that must be this multiplying the slope, right? So in other words, sigma A, twice sigma A is equal to E times twice epsilon EA. Or in other words, the alternating stress is equal to simply the Young's modulus times the elastic alternating strain. So this is the second relation that we find, which is again comforting because it correlates with our earlier discussion, which says that unloading is elastic. That's exactly what we're seeing here, except that a portion of unloading is on one side, the other portion of unloading is on the other side. So the triangle itself is not lying along a elastic unloading, but eventually when we overall look at the deformation and judge that this is the total strain, this portion of it is indeed associated with pure plastic deformation, and hence this must be pure elastic deformation. From that, we also again calculate that the stress change is associated with strain change through a linear relation where the proportionality constant is the Young's modulus. So it's again exactly the same thing. So now we therefore come back to the following question. Suppose one gives me the value of the total strain change, delta epsilon, or alternatively, the question is, suppose total strain amplitude is provided, and we would like to predict, right, at any stage of the game, if you like, what the corresponding stress amplitude is. Okay. Now, if I'd like to calculate sigma A, I know that it is E times the elastic portion of the strain amplitude, but the elastic portion is the total strain minus the plastic portion. So if I'd like to answer the question, what is the stress amplitude for a given strain amplitude? In order to answer that question, I need to know the plastic portion of the strain amplitude because I need the elastic portion to calculate the stress. So this question is equivalent to what is epsilon PA? And that's exactly the type of equation that we asked earlier in the context of the modeling of the stress strain curve. And in fact, we're going to now, as you will notice, follow an approach that is very similar to the Ramberg-Osgood model. So we need a model. We need a model because what we are given is the strain amplitude, and without being able to predict the plastic portion of the strain, I cannot calculate the elastic portion and hence calculate the stress. So the model will help me predict what the plastic portion of the strain is. And the model works just like the way it did in the Ramberg-Osgood case. We are proposing Ramberg-Osgood because it turns out that the way the cyclic stress strain curve looks is something that can be modeled with the Ramberg-Osgood relation. And the Ramberg-Osgood relation, remember, works as follows. Now, first of all, if we'd like to calculate the stress, then the stress is always the Young's modulus times the elastic portion of the strain. Of course, we're only referring here to the amplitudes because that's what's given. The mean, remember, is actually equal to 0. So this is always true. And what's also always true in the Ramberg-Osgood model, again, we're using that because it fits this type of curve quite well, is that the stress can simultaneously predict the plastic strain, in this case, the alternating portion of the plastic strain, through a power relation. But we say that this is also always true. Now, we had earlier introduced the coefficients h and n, so to distinguish them from the uniaxial stress strain curve, we're going to put h prime and n prime. In other words, the uniaxial stress strain curve, let's say this green curve, where we start with the uncycled raw specimen, might be modeled with the Ramberg-Osgood model with exponents h and n, but it turns out that the exponents we need to model the cyclic stress strain curve in general, they are different, and so we call them h prime and n prime. So in fact, let's highlight that. So these are associated with new values. And in fact, here, for instance, n prime is something that usually lies, remember, we want it to lie between 0 and 1, but here it's something that usually lies between 0.1 and 0.2. It's a narrower range than the exponent n for the Ramberg-Osgood model of the uniaxial stress strain curve. Now that we have these, right, let's go back to our original question. Given epsilon A, what is stress? And so the stress amplitude, actually. So, well, once we have the two portions, what I can do is I can sum these up and I can conclude that, well, so first of all, the total strain has an elastic part, epsilon A, which is sigma A over E, and it also has a plastic part, this part, which is sigma A divided by H prime to the power 1 over N prime. So now we have an indirect relation or a reverse relation because usually given the strain, I'd like to calculate the stress. So this naturally works in the other way. Given the stress, I can calculate the strain amplitude. But in any case, we do have a relation, and that was our goal. Okay, so why have we done all of this, right? The reason we've done all of this is to notice that what we're trying to do is we want to predict, or we want to make a relation between strain amplitude and number of cycles to failure. Earlier, we followed a stress-based approach. And in the stress-based approach, conceptually, we know the value of the stress amplitude, and if we have a good relation to the number of cycles to failure, which we do through the Basque-Cohen equation in the case of high cycle fatigue, then actually notice that provided this relation works, and we assume that it does, we assume that it's a good model, notice that as soon as I know the stress amplitude and the corresponding number of cycles to failure, through this relation I know the corresponding strain amplitude. And hence, if I have this information, then we know also the relation between the strain amplitude and life. Okay, so that's how it would practically help us. So we were trying to answer the question, well, how can I generate information or models for a relation between the strain amplitude and life? Well, if you have a model that works for the stress amplitude, then you can convert it to the strain amplitude through this information. That would be one practical scenario. Of course, I'm assuming that here that we have a good stress-based model, which may not be the case in the case of low cycle fatigue. Alternatively, notice that if we have a relation for strain-based fatigue, then solving for the corresponding stress implicitly implied by this equation, solving for the corresponding stress amplitude from the green relation, then we know the corresponding relation for stress and life. Okay, so this is how this information can help us. Now, either way, notice that this is just a tool. The real piece of modeling lies here. This is where fatigue modeling lies. So this is just a relation between stress and strain amplitudes. The model requires that we build a relation between the stress amplitude and life, which we did for the Basque-Cohen equation. And presently, we want to do the same between strain and the live number of cycles to failure for the case where those cycles are lying towards mostly in the low cycle regime. So this is where the modeling effort, of course, in conjunction with experiments, this is where the modeling effort comes in. So let us now concentrate on this portion of the relation. So how do we build a relation between the strain amplitude and number of cycles to failure? So we'll discuss that and move on towards a relation that is representative of strain-based fatigue.